Hello, my name is Graham Robertson, and I am the person that actually wrote the curriculum for building an ROV. So it's my fault. So I'm a science and engineering teacher, and I was fortunate to teach at a school with wonderful kids, and many of whom went on to be engineers, like Brian, who is an engineering student. And we found that having kids make mistakes, figure things out, and learn how to build gizmos was a great way to understand the world around them. So that's why MATE, Sea Perch are supported by these major universities, and we hope you have fun building your ROVs.
Hi, I'm Brian. I'm here assisting Mr. Robertson with the construction of the RV, so I'm doing a lot more of the technical stuff like the actual building and showing how it's done. I was one of his old engineering students. Now I go to college for engineering, as he mentioned. I participated in some of the MATE robotics competitions. I went to 3 international competitions and we did pretty well there, so hope you have fun on your ROV journey like I did, and let's see if it's a good course.
So this curriculum is designed for students who have not necessarily had much hands-on building experience, and they will need a lot of instruction on how to use tools. However, too much instruction gets boring. So I hope that you'll give the kids a chance to make mistakes and experiment before they actually attempt the really important connections they'll need to make. So the other programs that are listed in the curriculum are Sea Perch from the wonderful university, MIT, and the MATE, Marine Advanced Technology Exploration Program out of California. And these programs are far more structured, detailed, require team efforts, and each year new challenges are very difficult, and students have to put a lot of time and effort designing gizmos that can meet the new challenges. So this program is an introduction. If you have kids that have more experience, make sure that the ones with less experience get to build their fair share. And if the kids are making mistakes, then you're doing your job really well. Thank you. So now we're going to introduce the overall layout of all of the stuff that you have got ready to unleash the kids on.
So first step to build the RV is you need something to power it with. So that's what this is for. It's a big 12-volt power bank. Heavy duty, and we're going to use the cigarette lighter here, plug it in, powered, and this is going to run down to our control box, which we're going to put our switches into, which control our motors. So they're reversing switches forward and backward, and that's how we're going to control the RV, which is going to be run through the tether, which is this Ethernet cable, which it's got 8 wires in it, 2 for each motor. We're gonna run the power through that to the motors, which we're gonna use, which are these bilge pump motors. So you hook these up and they spray water up, and that's how you're gonna get thrust out of your motors, which we mount onto an ROV made of this PVC pipe, which we've got these cutters, and you can just cut it down to whatever size you want. This is obviously useless because it's so short. And finally, we've got our video, which we are going to display on this backup camera, which we are going to stick underwater. We got this display, and then there's a camera that somewhere in here, that you mount to the ROV, and then you can see where you're going. So it should all be put together with these components here. Alright, so got our wire hooked up to this big thing, and now we're going to get power going and complete the circuit. And oh, your wire has exploded. This is not what you want when you build an ROV. So, what has gone wrong here? Well, we've got no load on this circuit here. It's just power, wire, ground. So what's happened there is your resistance is very low. And when your resistance is very low, your current gets very high. And when your current gets very high, stuff like this happens. So, in order to solve that problem, we have things called fuses. So this here is a fuse. We're gonna cut the wire and expose some conductor so we can hook it up properly. And this, there we go. There we go. There's one end. And strip the other end. So there we go. We'll get more wire. And we'll strip it some more.
And so, Brian, you're going to hook everything in series.
Yes, everything is going to be in series. There's two ways to hook things up. Series, which is when wires are all in line, and parallel, when they're going next to each other. If you don't do it in series, the fuse isn't going to do anything, which is very important because this is the point of a fuse. It's a safety device.
So switches are always in series.
Yes, switches are in series, or else, again, they're not really going to do much.
And a fuse is sort of a safety switch.
Yes, it's kind of an automatic switch. It turns itself off when things go bad. So we'll hook this up to one end, and then we'll hook this up to our fuse. And this is the kind of fancy kind of car fuse where it's replaceable. So according to this chart, let's just get a 3-amp fuse. This is gonna go into our thing here. Alright, that should be in. Now we hook this up to our other end here. And now when I hook this up, nothing happens. This is good. We want nothing to happen because that means our wire isn't exploding. Alright, so to summarize, we first tried the wire without a fuse, and it melted. Then we tried the wire with the fuse, and the fuse blew, but the wire didn't melt it, and so all of our electronics would be protected by just having the fuse go. So, how do we reduce this amount of current so the fuse won't blow at all, and we can just continuously use our electronics? Well, we need more resistance or a load. In this case, it's going to be our motor for our ROV. These will reduce the current used. So what we're going to do is we'll put our motor, Bilge pump, in this bit of water here so it doesn't fry itself running on air. We'll get our conductor here. We'll hook our fuse up because we are nice and safe. And we will then strip some wire off of our bilge pump. I don't leave much to work. now, we've got our load on it. If we hook this up, we should just get continuous usage of our motor. Look, it's running. The fuse isn't blowing, so we're under our fuse threshold of current, and we have no problems. So this is the goal with our ROV here. Alright, so here we're going to do a little bit of a covering of Ohm's law and why this is important for building an ROV. So, you know we have a fuse. We don't want it to blow or else the entire thing's going to shut down. And we know we have this 12-volt power supply. So how can we tell if what we're running on this RV is going to draw more than 15 amps, which is the, well, that's the specific fuse we use for this, because in our case, we're using these banana plugs and these plugs have a 15 amp fuse built in. It's not like these other ones where we can throw in any size fuse we want. So if this goes, then we're kind of screwed. So in order to tell if we're going to take over 15 amps, we can do some quick math on this thing called Ohm's law. So Ohm's law is that the voltage you're using is equal to the current, which is shown by an I, times the resistance, which is R here. Now we can just do some easy math here and figure out that our current is equal to the voltage divided by the resistance. So this is what we want to find. We know we're running 12 volts. So we can do 12 volts over, but what's our resistance? Well, our resistance in this case are our motors. And how can we find the resistance? Well, there's these nice things called multimeters. They basically are a fancy tool here that you spin this dial and you can read different electronic components. So you can read voltage. So just to make sure that this thing is running on 12 volts, we can take this and it's falling off because the cable's too short. I'll twist it up. We can read the voltage coming out of this. So one contact there, and I'm reading. You gotta spin the dial so you read the right thing. I'm currently reading resistance of that. It's not what you want. And you know what? I'm just gonna get on the right contact. There we go. This is actually reading 13 volts because it's very well charged. But in this case, well, 13 doesn't make much of a difference. And then spin the dial and you can read the resistance of an object. So here we've got our bilge pump. We put the leads across the two things we're going to hook our motor up to. And it comes out to 5.1 ohms.
Or 4.9.
Or 4.9 or something, I don't know. This isn't the greatest multimeter.
5.
It takes a while for it to make up its mind, and then sometimes even then it doesn't. We'll call it 5 for ease of math. 5, then that's the symbol for ohms. Equals our current. So now we do some math on any calculator. In this case, I'll just use my phone. Oh, divided by 5 is 2.4. So each one of our motors is going to draw 2.4 amps. Now, we have 3 of these motors, so 3 times 2.4 is going to be 9.2 amps is our total current. Now, we've also going to have a camera on there.
7.2.
7.2?
Yes.
Ah, yes. College student who has done many years of calculus, still can't do basic multiplication. It happens to everyone. So 7.2 amps is our total current from the motors, but we also have a camera. However, the camera isn't pushing masses of water, it's just filming, so it doesn't really draw that much current, and you can basically call it 0. So in this case, this is all the current that our ROV is going to be drawing at any effective time. That's if you run all 3 motors at the same time, which isn't going to be happening all the time. And obviously, that's much less than 15 amps, so there's no chance our fuse is going to blow.
So what is electricity? Ohm's law, current, amps, volts, it all sounds very mysterious. So let's do a simple experiment to find out what electricity is. So here is a plastic bag from produce department. And now we have a strip of plastic. And I'm going to rub the whole strip the same way. And now, abracadabra, what is happening here? Two things. It looks like there is repulsion and attraction. I'll rub it again. Today's a sort of a damp day and we're near the ocean in beautiful Southern California. There we go. So what is happening? All of this plastic was rubbed the same. When I rubbed it, I stripped off electricity and charged this plastic. So we can see that like charges repel and opposites attract. So how many kinds of electricity are there? Two at least. And what are you going to call them? Yes and no? Up and down? Well, how about plus and minus? So what is electricity? Well, the answer is this thing is made of electricity. You are made of electricity. All matter is made of electricity, and we disguise it by calling them atoms made up of protons, electrons, and neutrons. Every single thing is electricity. Now, plastic grabs its electrons and I rub them off with my fingers. But it's an insulator, it won't flow, so we call this static electricity. And it might shock you to find that this is about 20,000 volts of static electricity as shown by this great distance at which it attracts and repels. So if you want electricity to move, if you want electrons to escape atoms and wander around freely, you must have metals. So everything we have here is metal inside non-metal. The metal lets the electrons flow, and the non-metal part, you can rub it and give it a static charge, but it won't let electricity flow. So what's the answer to the question? What is electricity? And the answer is all matter is made of electricity, and you learning how to pump it around, how to measure it, helps you understand the universe and yourself. You are made of electricity. Your brain makes electricity. Your muscles work with electricity. All matter is made of electricity.
All right, so one of the big problems we have with this ROV is we're running the power through this Ethernet cable, which at first glance, you can see it's pretty thick, but this Ethernet is not just one wire, it's actually 8. So if we cut the end off, which we need to do anyway, you can see in there are 8 tiny little wires. And we're going to be running all of our motors off those tiny little wires, which is quite inefficient and a little bit dangerous. But it's good enough for this basic ROV. Now, I was on a high school ROV team for 4 years, and we use Ethernet, but we also use other stuff. So the way we ran our ROV is much bigger and competed in these big competitions is we used this thing, which is what we call the brain. This is what controls the ROV. So what we did is we used the Ethernet, but that was purely for telling the ROV what to do. We also ran 2 big speaker wires that are, each wire alone is about the thickness of this one Ethernet. And that was just for power and for ground. So we could run way more current down there. We'd pull upwards of 20 amps at any given time. So the way we do that is we use this to tell where that big power where to go. Obviously, we can't split that very efficiently. So what we have here is these all here are motor controllers. These are what do the actual splitting of the power and tells the power where to go. Here is basically a little computer. It's called an Arduino, and we write code and it runs on this. So we actually control our ROV off of a PlayStation controller. So we have many more buttons and we can tell it where to go, up, down, left, right, strafe, forward, back. So the PlayStation controller talks with this, or more accurately, this talks with the PlayStation controller, and then, depending on the input, tells which one of these motor controllers to activate. And then, from there, these get the 12-volt power from the big speaker wire and send it to the motors based on the dinky little 5-volt power that comes from the Arduino. So basically, it takes this, gets a command from the controller. It sends a 5-volt signal to one of these, and this, when it gets the 5-volt signal, sends 12 volts to the motors. And that's how we run the ROV. And it's not just motors, we got a claw, and we have other payload tools that are sometimes necessary, like suction, or we can push water through with some bilge pumps. It's a lot more going on.